There's going to be two types of edges. The first type we'll call clause edges because these are defined by the clauses. The second type are variable edges. Let's begin with the clause edges. Let's consider a clause of size 3. So here's a clause which is x1 or x3 bar or x2. In our graph we're going to have 3 vertices corresponding to the 3 literals. So this first vertex corresponds to x1, this second vertex corresponds to x3 bar, and the third vertex corresponds to x2. Now some of these literals might appear in other clauses. For example, if there's another clause containing x2, we'll have another vertex corresponding to x2. So there are multiple vertices corresponding to the same literal. Now, how do we encode this clause? Well, we simply add a triangle. We add edges between all pairs of these 3 vertices. In other words, we add the complete graph on these 3 vertices. What if we had a clause of size 2? For example, x4 bar or x5. Then we add 2 vertices corresponding to these 2 literals, and we add an edge between them. Finally, if we have a clause of size 1, for example, x1 bar, then we just add a singleton vertex by itself. This construction, the key property, is that an independent set S in this graph is going to have at most 1 vertex per clause. If you look at these 3 vertices, we can only include one of them because there's edges between all pairs. Now recall our goal was to find an independent set of size at least m. Since every independent set has at most 1 vertex per clause, in order to achieve our goal of an independent set of size at least m, this solution has to have exactly 1 vertex per clause. Now this 1 vertex per clause will correspond to the satisfied literal in that clause. Now there may be other satisfied literals in a clause due to other copies of that literal in other clauses. But this property that we have exactly 1 vertex per clause will ensure that we have at least 1 satisfied literal in every clause. And therefore this solution, this independent set, will be able to relate it to a satisfying assignment for this original formula. Now what happens if I take an independent set containing this vertex corresponding to x1 and this vertex corresponding to x1 bar? Well, if this is the graph, this is in fact an independent set in this graph. And I can take one of these 2 vertices, and then I have an independent set of my goal size of 3. Now a natural way of converting this independent set into an assignment for the original formula is to satisfy each of the corresponding literals. So to satisfy this literal, I set x1 to be true. For this literal, I set x5 to be true. For this literal, I want to set x1 bar to be satisfied, which means I set x1 to be false. Now I have a contradiction. This is not a valid assignment because I'm setting x1 to be true and I'm setting x1 to be false. So I want to ensure that my independent sets correspond to valid assignments. I never try to set a variable to true and to false.